You just heard from Eric and Kix about Cloudera Flash. In parallel, the all-flash arrays are hitting a wall. I'm here with Tabrice from our software engineering team, and we're going to dig into those challenges.
So we kind of have four main challenges with our all-flash arrays as we grow. One of the phenomena we're seeing is that the density of drives is getting much larger. We used to have SSDs on the order of 1 terabyte. Now we're seeing SSDs on the order of 15 terabytes. So as we grow, the problem that we're seeing is we're not getting much more performance as we grow in capacity.
And in fact, it's decreasing precipitously. So isn't that effectively what killed hard disk drives?
Exactly. And what we're seeing now is as these SSDs get larger and larger, we're starting to reach a performance capacity relatively close to hard drives. One of the main reasons for this is what we call this very small pipe. We have a limited ability of driving I/O to these larger devices. And as an analogy, this would be like having a 100,000 person football stadium with one door entry into it. Like you could really fill it up, but it's going to take days and hours.
Yeah, so you've got a small pipe, big flash behind it. You're not really able to take advantage of it.
Yes, exactly.
In addition, there's a lot of disk emulation software that's inside each one of these SSDs. That's doing the flash translation, doing the allocation, garbage collection, encryption. All of these SSDs are acting independently within your all-flash array. This also leads to the black box effect of an SSD. Because it's an independent device, most of the times an SSD is going to deliver very fast performance on the order of about 100 microseconds. But every so often you end up with very slow performance as well, about 20 milliseconds or even higher. And what that ends up doing is basically injecting performance variability into your all-flash array. Combined, these challenges effectively mean that it limits your consolidation value on that all-flash infrastructure.
On top of that, our software engineers end up spending a lot of cycles trying to invest in hiding and masking these things. If we didn't have these problems, we wouldn't have to spend so much investment in there. So here's where we let you in on a little secret. All flash arrays really still have a lot of disk in it. We've got disk-based protocols, we've got disk-based interfaces, and we have disk-based emulation software. Exactly. Why do we want all this if we're really an all-flash array, right? What if we can get rid of this software? We can get rid of these interfaces and we can get rid of these protocols.
So if you could get rid of all of that, what it would mean is essentially the array software could communicate to that back-end flash directly over high-speed links. And that global visibility would essentially enable it to be much more intelligent in how it exploits the full value of that flash or whatever silicon comes next.
And this is exactly what we did in 2016 with the introduction of FlashBlade. We've got raw flash and NAND on the board that we directly connect to through a high-speed, low-latency interconnect with multiple lanes and our Purity software driving the whole thing.
That's pretty awesome. What if we could bring that to our flash array? Today, we're super excited to introduce the Directflash module. It's the world's first software-defined flash module.
Software-defined flash module, that sounds like a bunch of marketing stuff. What does it really mean?
Well, let's dig into that.
All right, let's do. Okay, so let's take a look now again at the way the world was before Directflash. Again, we had SSDs and we had all of that disk emulation software sitting all inside each of these SSDs, all making decisions locally about what that drive thinks is best at that point in time. On top of that, in the old world, Purity is also trying to make decisions about garbage collection and block management as well. And those two can conflict in times. The SSD doing what it thinks is best and Purity thinks what it's doing is best. But with Directflash, we've got a single global instance of the software for managing the flash. And we don't have to worry anymore about conflicting opinions as to what is best to do.
So basically, all of the software that was running locally within each individual SSD, we've taken that software, moved it up into the Purity operating environment with Directflash software, now optimizing globally.
Globally, exactly. So our Directflash software is really divided into three components. The first is the adaptive I/O control. And when we say adaptive I/O control, what we mean is that we have the ability to directly write down to the physical pages on our flash. There's no more virtual to physical translation happening underneath the covers. So we know exactly where it's going, exactly what its lifetime is, and we can write in the optimal sizes for flash.
That's right. We now have the direct visibility into the queue of each flash die, so we can actually do all the way up to 128 parallel writes,
Exactly.
whereas previously used to be 8 or less.
Exactly, and also schedule writes and reads according to their best performance to whatever lane that it is good for it. The second aspect of Directflash is smart endurance. And when we're talking about smart endurance, what we're really talking about is the ability to control movement of the data within the flash. With SSDs, what we had is drive level garbage collection that could move data around underneath you. And what that meant is that for every write that you intended to do, you could actually be doing many more writes on the back end. And that really wears the capacity of your flash. So with our smart endurance capabilities, we have the ability to reduce our write amplification factor to practically none. The third one is predictive resiliency. Because we actually build this flash, we have about 1,000 times better visibility all the way down to the flash box. This gives us better telemetry as well as failure bad block detection. And along with this,
Yeah, when you combine it with our machine-based predictive analytics that are built into Pure One, it essentially means that we can predict if anything is about to happen, and we can fix those issues before they actually occur. So we just heard about globally software-defined nature such that all of Flash is now being optimized globally within the Purity operating environment. It's also connected with 100% NVMe. That means Purity now has direct access over these high-speed, massively parallel lanes. There's also no hidden flash. Now, with the Directflash module, Purity has access to 100% of that flash that's built into the flash modules. With the visibility down to the individual queues of a flash die, and with adaptive I/O scheduling, we're able to now deliver deterministic latency with the Directflash module. And the last area is that it also unlocks unprecedented levels of density. The Directflash module is ultra dense. With 18.3 terabyte Directflash modules, we believe they're going to be one of the densest in the market.